By the way, there are some new faces. You want to introduce yourself?
Hi, my name is Krishna. I'm Indian. This is my
Are
first
you
semester here.
in the undergraduate program or in the graduate?
Program.
Okay.
Yeah.
Okay.
So, I like computer programming.
You think are you interested in competing for the competition?
I don't think so because I've
You-
done in my undergrad, but
You may not satisfy the requirements.
no, I satisfy requirements. I've gone through that, email, all the stuff.
Uh-huh.
But I think I'm not in a pace to compete with these folks now because
Well, you're really feeding the egos of our friends here.
but that's a fact. So I'm not in that level to compete with everyone.
Well, the competition is a good experience, and so you may want to consider just going to see what it's like, what the environment is like, what the experience is like, and whether you really like that thrill, the adrenaline rush.
Yeah.
So you may want to consider this, but we can talk more. You, sir, you want to tell us?
I came today. Actually, I was hoping to be part of this last spring, but then the COVID happened and everything blew up.
Yeah.
So I'm here to see if I can learn something and be part of the group. But definitely learn something.
You think you'll be competing with us?
I want to see if yes.
Yeah. So take a look at the eligibility criteria. Make sure that you're going to be fine. Okay. And if you are, I'll find you a team to be part of. Okay. All right. So we were talking something about combinatorics last time. So I'm going to quickly try and wrap that up. If you remember, this is what we were talking about. Yeah, we talked about a whole bunch of different counting related questions. Yeah, here you go. So these were some of the problems we looked at. We looked at how many ways you can form a team of k people, how many ways you can line up the different people, how many ways you can form different groups. There are a whole bunch of questions, right? So I'll let you go back and look at it if you weren't here last time. But then slowly the problems got harder and harder. And finally, we were starting to look at the most general question, which was, how many ways can we partition a number n into a bunch of integers that add up to n, right? And what we said was that there was this very strange connections with all sorts of nice mathematics, and we're going to try and connect with that. So let's assume that n is the number that we are trying to partition. N is, of course, an integer. We're going to assume that P of n is the number of different ways we can write n as a sum of other positive integers. Okay? Remember, they have to be positive. You can't use negative, otherwise you'll get infinite possibilities. So it turns out the first thing is to try and write down recurrences. And there are simple recurrences that you can kind of figure out. So the first one says the number of different ways I can write down n as a sum of other integers is, well, first of all, there are, I can find number of different ways I can do n minus 1 and then add 1 to it, right? So that's the second thing over there. The first one is, how many ways can I write n as a sum of integers without using the number 1? All right. So in the first one, you're not using ones. In the second one, you're going to use 1, 1, and then figure out how many ways to partition n minus 1. If you add these up, that should give you P of n. I can also write it in another way. I can write it as the summation of P of n comma k, where P of n comma k is the number of ways to write n as a sum of k different integers. Okay. so these are all different ways to kind of write down the relationships. This is only partly a recurrence relation. It's not quite completely a recurrence relation. But you could now write P of nk also in another way as a nice recurrence. And this recurrence comes about if you use the number 1. If 1 is part of your sum, then you can remove that 1, and you will have k minus 1 integers to add up. If on the other hand, if you don't have 1 in your sum, right? If there is no 1, then all the numbers are more than 1, which means I could reduce each of those by 1. And since there are k such numbers, I would now have to figure out how to partition n minus k into k integers. Let me see if I can explain it more clearly. So let's say that I'm trying to write down the number 7. 7 could be written as 3 plus 2 plus 1 plus 1. Or I could write it as, let's say, 4 plus 3. Okay? If I consider this case, then this has a 1 in it. So that's counted under this, because I can remove one of the 1s. I have k minus 1 numbers to add up, and they have to add up to n minus 1. So that's this count here, right? What about this guy here? If I look at this case where there are no 1s, I could reduce each of these by 1. Because there were no numbers that were already 1, when I reduce each one, I still have everything that's going to be 1 or more, right? There are not going to be any zeros here. So now I still have k integers, except that I need to sum up to n minus k, because I've removed 1 from each of these k guys, right? So if you add up these two, that'll also give you p of n comma k. Clear? So these are all different recurrences, and they all help you to compute your answers. In fact, you can also write a recurrence for p of minus 1 of n, which is the number of ways to write n without using 1s. Right? If I'm not allowed to use 1s, then all my numbers are larger than 1. So I can reduce each one by 1, just like I did over here. And so it's the same as n minus k comma k. OK? So that's another way to write down the recurrence. So all of these give you recurrences, except that they all seem to be kind of related to each other.
Where does the k come from? Is that something you choose?
K is an arbitrary number. K, you're going to try all possible values of k. All right? So you're going to try, what if I have only one number? Well, that's only 7. What if I have two numbers? I can do 6 plus 1, 5 plus 2, 4 plus 3, and so on. What if I have 3, and so on and so forth? So that's another way to approach this, saying, OK, let's start by figuring out how to write this as a sum of one integer, then 2, then 3, then 4, etc. And in each case, you divide this by saying, what if 1 is used and 1 is not used? So these give you nice recurrences, and you can now fill up the tables using these ideas. And you can see here, you just have to figure out some of the early numbers, and then after that, it kind of fills up quite easily. If you're not allowed to use 1, and if you want to sum up to 1, there's no way of doing it, so that's 0. If you want to sum up to 1 and 1 is allowed, there's only one way to do it, and that's the number 1, right? If you want to sum up to 2 and you're not allowed 1s, then the number 2 itself is the only way to do it. Whereas here you could do either 2 or 1 plus 1. So, and then you can also write, this is if you're using one number, if you're using two numbers, and so on and so forth. If you're using one number, all of these are going to be just 1, right? If you're using 2, things change, but all of these can be written down using that formula there. Okay? So it's possible to fill up these tables and figure out whatever number you want. All right? And the recurrences are work, they're clean, and it's possible to write a program for this. What we were trying to do last time was to see how to do this using these amazing generating functions, right? That's where we wanted to go. So the method of generating functions says, let's try and write a polynomial, a strange-looking polynomial that looks like this, where a polynomial we know has terms with x to the 0, x to the 1, x to the 2, x to the 3, and so on, right? So it's a polynomial in x, except that the coefficients are the interesting parts. The coefficients are exactly the counts that we are interested in. So the coefficient for x to the 1 will give you p1, coefficient for x to the 2 will give you p2, and so on and so forth. So this is a fictitious polynomial that we are defining, that we are constructing, that contains the interesting information that we really want, which is p of n for each value of n. What we see, very strangely, is that this polynomial is exactly the same as multiplying these strange-looking polynomials. This is one where you have 1 plus x squared plus x cubed, and so on. So you have every degree of x, but all the coefficients are 1. Here you have every alternate degree of x, 1 plus x squared plus x fourth plus x sixth, and so on. Again, coefficients are 1. Here you have all multiples of 3, 1 plus x cubed plus x sixth plus x ninth. And then you have 1 plus x fourth, x eighth, and so on. And this thing seems to go off to infinity. What is nice is that when you imagine actually multiplying all these polynomials and writing them down, the various terms that you get look exactly like what you want, which is the generating function that you wrote down. All right? Now, starting with that, it turns out you can do lots of useful, interesting things. And the first thing is that each of the terms here can be written in very compact forms. So 1 plus x squared plus x cubed, and so on, can be written down as just a 1 over 1 minus x. The next term can be, the next factor can be written as 1 over 1 minus x squared, 1 minus x cubed, and so on. So it turns out that the polynomial that we really want is simply a product of all these guys. But of course, it's an infinite product. Doesn't matter, because whenever we want something, we will only want the coefficients of something finite. So even though it looks like it goes off to infinity, we don't have to worry about that. But its behavior becomes nice only when it goes off to infinity. Otherwise, it's not so useful. So this is the trick. And then from here, the question was, what do we do next? And it turns out that there are lots of different properties you can prove. I am not going to get into all of these. We sort of talked about it last time, but here is the general thing. How do you use these generating functions? And so the way this works is you can do some differentiation. You can do some differential calculus on it and figure out how to write down more compactly what goes on with them. But then at the end, you're going to expand both the polynomials and equate the appropriate coefficients. So the coefficient of x squared here must be the same as the coefficient of x squared there. Coefficient of x cubed here must be the same as the coefficient of x cubed here, and that helps you to figure out what the answers are. Now we'll look at a couple of simple examples, and then I will leave this part. So for instance, here is one way to do it. One of the formulas says that P of n is summation of sigma k P of n minus k. Here, sigma of k is the sum of the divisors of k, which means all the numbers that divide k. Okay? So if k is 6, all the numbers that divide k are 1, 2, and 3. So you multiply that by P of n minus k, and you add that over all possible values. Okay, anyway, it's some formula there. Okay. So it turns out I can use that to compute P of 4. All I do is plug in the values. Okay. Same thing with P of 5. I can do the computation if I use this formula. On the other hand, if I actually use the polynomial and spread and open it out, this will give me another way to compute it. So for instance, if I want to compute P5, remember I have this infinite polynomial, but I don't have to go and compute everything because I only want the coefficient of x to the 5. And if I want x to the 5, I only have to take the first 5 terms of that first factor. I only have to take the first 3 terms of the second factor, then 2 terms of 3 more factors. I'll forget the rest because all that will only give me terms that are higher than x to the 5, right? And I will actually go and multiply these, and this somewhere there, it'll give me the coefficient of x to the 5, because no other term is going to contribute anything to the term x to the 5. So if you go and do a little bit of algebra here, you can figure this out. Does that make sense? So that's really how you go about doing this. So I kind of sped this up, but you can go and play with this a little bit more and try and figure out. If you have questions, I'm happy to go over something again later on. Okay? Are there any questions here? This probably went a little too fast, right? It's okay? Yeah. So there are lots of different directions one can play with here, but in the end, you're either equating polynomials on the left and polynomials on the right, or you're doing some kind of differential calculus to make things a little bit easier. Yeah.
Where do you go from here after you expand all these things?
Yeah. So here, if I want the term for x to the 5, I can take x to the 5 from here and pick up 1s from all of those. That'll be one way to get x to the 5. Another way to get x to the 5 is take this x to the 4th and take the x from here. Okay. You can actually do the expansion, which is not such a bad thing, and you'll see exactly how x to the 5 shows up. Okay. X to the 5 could also show up by this x cubed multiplied by this x squared, or this x cubed multiplied by that x squared. So there will be 2 contributions. Right?
And that ends up giving you all the different ways of
Essentially, it's doing what you would have done by hand. But you can automate this. You can write the program for this and let that figure it out rather than doing this by hand.
If we were to, like you said, program this, we'll be using that formula that you showed us, the P of n is equal to P of n minus k, k plus P of n.
That's a different approach altogether. That's a recursive. That's a recurrence relation approach. This is a different approach. This is a polynomial approach.
So, but we can, if we were to program this, that would still work, correct?
Both of them would work.
Okay.
Yeah, both of them would work. Here you have to write code for multiplying polynomials. There you're going to write program for the recurrence relations. Okay? Yeah. So that's roughly the general idea. Last time somebody asked me this question, I had this question where we said, how can we change a $1,000 bill in a country where we only have $9 bills, $17 bills, and $31 bills. And it turns out that there is a very neat answer using what we did here, and that is you just compute this polynomial, where you have 1 divided by 1 minus x to the 9th, 1 divided by 1 minus x to the 17th, and 1 divided by 1 minus x to the 31st. Remember, this is the same as 1 plus x to the 9th plus x to the 18th plus x to the 27th, all the multiples of 9. Here it's all multiples of 17. Here it's all multiples of 31. And then you have to compute the coefficient of x to the 1,000 in that product. It looks hairy, but it's possible to program this and let it figure it out. Remember, there are only 3 polynomials to multiply, not that big a deal. Okay? Okay. Yeah. This general approach with generating functions has lots of applications. So if you ever feel interested, I'd be happy to point you to some nice material that'll help you. Okay. With that, I'm going to move on to a different topic. So are there any questions with this counting stuff? Integer partition is a really important problem. Almost every other year something shows up with this, so it's not a bad idea to try and write some code and get it ready, print it out, and take it with you when you go to the competition. Okay? Or there's probably ready-made code elsewhere, so you can just pick it up. Okay, so that's done. We're going to then move on to the NAQ competition. So I kind of looked at this, and there were 2 people who tried problem A and problem C. These 2 were easy. Looks like almost everyone got it. There's no point in me wasting time there. This one, about 3 people got it. The others didn't. I could have looked at this one. Instead, I picked this one here, where 3 people tried it and didn't succeed. So at least more people are now exposed to it, and I thought this would be a good problem to look at, and that's what I'm going to tell you about. And this is the pizza party problem. Yeah, you guys read the problem? And have you solved it yet since then, or you tried?
Splitting using regular.
Okay. All right, so let's talk about some possibilities. But before that, there are newcomers, so I'm going to let them read the problem. Were you at the competition, Michael?
Oh, no. No.
You are
I
not at the
wasn't.
qualifier. Okay. And you, sir, you want to introduce yourself?
Yeah. Hi, everyone. My name is Seraphim Dominguez. I'm a grad student.
Okay.
Yeah.
But you've checked your eligibility, and you
Yeah.
think you might get through that?
Yeah, because I'm a first-year grad student.
Okay. All right. Okay. Good. That's good. Yeah. So take a look at this problem. So one of you wants to summarize the problem for me? You want to try it?
All right. Wait, the actual statement, or do you want me to go?
Just summarize, yeah.
All right. So for the input, they're going to be giving you a toppings for pizzas. Some of them are going to be what is the word they use? Absolute.
Yeah.
So they will tell you the exact topping, like pepperoni or sausage. But other ones are implicative.
So you could have, so for instance, at this table, there were these choices. There's peppers, there's spinach, there's feta, and then there's one statement that says, if spinach and olives, then I also want tomatoes.
Yeah. And there's also ors as well. So
Right.
you can have an implicative of just ands when you need all of them, or you can have one where it's ors when you're using one topping
Right.
from that. Or
And then what are you required to do?
and then if you meet all those requirements, then you could get your then topping.
So there's an easy way to meet all the requirements, order all the toppings. So
Yeah.
what's wrong with that?
You're trying to minimize it, because let's say for or, you don't want to get all of them, if you can just satisfy with this one.
Are we good? Yes? Okay. Not this, sorry. So for the newcomers, before I go off to pizza party, just to make sure, the competition, the big competition is on March 5th, and it's right here across the street. But we'll have to register you, we'll have to put you in a team, so be engaged with us, make sure that you let us know, and set aside the date. Tell your family and whoever is might have interest in your time that you're going to be busy that day, all day, because it's a morning to evening affair. These are fun events, so I really recommend that you try this at least once in your life. And then from now until March 5th, we are going to be intensely practicing for this competition. That's our plan. And the goal is to make FIU look good. So we're trying our best to do that. I hope you will work with us. There are several training sessions. I can never remember who does what. So Tuesday is David. Okay, Tuesday we have a session with David who does more elementary questions. Then Wednesday is with Joseph, and he does follow up on whatever it is. So a little bit harder, presumably. And then Thursdays it's me over here talking about whatever the heck seems to come to my head. And then Friday we have Lazaro, who goes over some of this material again if people have questions. And Saturdays we do mock competitions. So we're here 5 days of the week, working intensely, at least until March 5th. We'll see after that, to make sure that we put up a good performance on March 5th, right? And remember, every team will have 3 people, but you will have access to only 1 computer, which means that one person will be coding and debugging. The others are going to be figuring out how to solve the next problem on paper. So you need skills. You need all sorts of skills, and you need to be fast. So that's why it's exciting. That's why it's fun. Okay. To a large extent, there are lots of competing teams, but to a large extent, you're competing against yourself, trying to figure out how you're going to solve this problem. I hope you join us and have fun. There was a qualifier competition. I know many of you did not make it to that, but it's you can still go and look at those problems. In fact, we're going to go over a couple of those today. The pizza party problem is from there. There are practice events every Saturday and Sunday until March 5th. And in case you're not able to find the link, hey Joseph, I'll email me and I'll send you the links for the competitions. Okay, so
Professor.
Yeah.
So the mock competitions on Saturday, I guess they're online then.
yes, everything is online. Yeah.
Yeah, so for now, we changed it up a little bit, because I know last time it was from Saturday at 12 to 5, but it seemed like a lot of people have troubles with that issue. So we do Friday, it starts at 12, and then during my lecture, I help you guys program at least one problem, just to give you some motivation or some momentum, and then it goes all the way up to Monday. So now you have 3 days, Monday at 12, so you have 3 days to solve as many.
To solve whenever you want to solve.
Yeah, yeah.
Okay.
So hopefully that gives you guys more opportunities to really try and apply what you learn.
Okay. All right, that's great. So here's the pizza party problem. So as Lazaro explained, you are the waiter, or you're the person serving this table, And you go to this table, and there is a big party over there, obviously, and each one gives you requests. And these requests are either in the form of an absolute request saying, I must have anchovies, yeah? Or it might be something a little softer that says, hey, if you're going to order spinach and olives, I better have some tomatoes on it as well, okay? So there are at least two kinds of requests. There's also a third one where you could say, if I have spinach or olives, I still want my tomatoes, yeah? So there are three kinds of requests: these absolute requests or these if statement requests. And the if statement request may either use and or. And the then part always has only one item. Okay, there's only one consequent, it seems. So this is these are the conditions, and if these conditions are satisfied, then you must have this. All right? That's what's given to you, but of course, the real problem is that you want to minimize the number of toppings that you serve on the table. Your job is to satisfy everyone. If it means having to get all the toppings, so be it. So over here, peppers and spinach and feta, you don't have a choice. These are absolute requests, so you're going to need at least 3 toppings for that table. However, here it says if spinach and olives, then tomatoes. What do you learn from that? If you're going to order spinach and olives, then this person wants tomatoes. If you only order spinach and feta and peppers, you're not ordering olives. So therefore, this condition is not satisfied. Therefore, you, as somebody who's going to pay for this pizza, doesn't have to order tomatoes, right? Which means that you can get away with only 3 toppings and everyone will be satisfied. No one will complain, okay? So your job is to make sure no one complains. Any questions about the way the problem is set up? All good? Okay. There's also a couple more examples here. We can go over them later. So the idea is that you want to satisfy all the constraints at the table, and the constraints are of 2 types, and either way it doesn't matter. You have to make sure that they are satisfied. And of course, you want to output the minimum number of toppings. You want to know what's the minimum number that you can get away with. So here's a simple approach. You can simply try all possible combinations of toppings, and among all the ones that work, that satisfy people, you can just pick the one that has the smallest number of toppings. What's wrong with this approach? The time complexity, and that's because the time complexity would not be a problem. However, in this case, you're told that you can have up to 500 toppings. So how many different combinations are we talking about?
I'm not sure that's right.
Factorial comes in permutations, right? Factorial shows up in permutations. With combinations, it's 2 to the 500, okay? So just make sure in your head quickly whether it's permutations or combinations, and then that'll become clear. So in this case, there are 2 to the 500 combinations, because each topping, you can either have it or not have it. So that's 2 choices. So you have 2 times 2 times 2 for 500 things. That's 2 to the 500, right? 2 to the 500 is not something you want to mess with. 2 to the 500 is roughly, 2 to the 10 is 1,000. 2 to the, so you're talking about 47 zeros followed by 1,000, something like that, okay? So it's some absurd number that you're not going to be able to work with for this problem. So therefore, you have to do something more. Well, you're also told, by the way, that there could be up to 1,000 constraints. And the constraints also have to be processed, so that's an additional cost. So there's no way you're going to look at all possible topics. That's not an option. Forget it. Get it out of your head and move and figure out the next. Now, there are different kinds of logical statements. The first says things like, well, let's look at possible if statements. One possible if statement says, if I have spinach, then I better have pepperoni. This is the easy one. And this, how exactly do we understand this? What exactly does this mean? What kind of choices does it give you as somebody who has to make choices about the toppings? Can somebody explain? Yeah?
If somebody orders spinach, then there has to be one with pepperoni.
Correct. Well, so how much do I have to pay for if I have to pay for toppings?
If it's not spinach, then just one. Well, no, yeah, if it's just not spinach, just one.
Which one?
The non-spinach topping.
Non-spinach is not a topping.
Were there statements like this in the problem?
Yeah.
I thought it was only.
You could have, it says that you could have as many things you're doing an and of or of, so it could be one.
I believe it's 2 toppings, but you couldn't go around that statement.
You're saying you're going to need 2 toppings.
Yeah, if you get spinach, or if on the other hand, you could get 0 toppings.
Well, remember, I want the minimum. I'm a cheapskate. I don't want to pay for 2.
0, I guess.
So it's 0. Can I get away with 0? Clearly I can, right? Because I don't have to, as long as I don't get spinach ordered, I'm free. I don't have to satisfy this person. In fact, the person would be satisfied because the spinach is not there. Right? So I can get away with 0. That's what this means. But another way, you really need to understand this a little bit differently. What this says is, if you're going to have spinach as a topping, you better have pepperoni. Right? That's what it says. And for those of you who have taken the logic class, this is really the same as saying not S or P. Not spinach. You either don't order spinach or you got to order pepperoni. Okay? This turns out that this is the best way to write implication statements. Any if statements are best written this way. And this will take care of all the possibilities. In fact, these 2 are equivalent, and all cases are the same with both these possibilities. Okay? Now, let's look at something slightly more complicated. What if I have the ones that you were referring to, where if I say, where the statement says, if spinach and feta, then I need a pepperoni. Well, I can do the same thing here. It says if S and F, spinach and feta, then I want pepperoni, right? This is the logical way to write this. Clear? If I write this without the implication, then it becomes not of all of this or this, right? But not of all of this is the same as not S or not F. And becomes an or when you pull out the not sign. So now I could even remove these parentheses, and I essentially get not S or not F or P. I just need one of these and I'm fine. Is that clear?
Wait, so the bottom one you're saying is the same as so if spinach and feta then pepperoni.
All of these are the same as this. Yeah, this whole bullet is the same.
Oh, I guess I just wasn't seeing it at first. So okay.
Yeah, this bar goes over all of this. When you open that out, the and becomes an or. If you're saying, I don't want you or him, that's the same as saying, I don't want you or I don't want him.
Oh, okay.
Okay?
Right.
All it's saying is, I don't want the 2 of you together. That's all it's saying. Is that clear?
Right. Yeah.
But it's okay if one of you is there.
Okay.
The only thing that's not allowed is both of you together. So the only thing that's not allowed is spinach and feta together. But it's okay if I want to put spinach or feta.
In the problem statement, I just don't like it over here.
Yeah.
They mentioned something about the form of all the implicated references.
Yes.
I mean, from what I understand here, it doesn't include the if spinach, then.
The first one? Okay, fine. If you're happy with that, that's fine.
Oh no, let's do it like that. I was just wasn't sure like if I am the one who's misinterpreting this or not.
I don't agree with you, but I can check this one more time. Yeah, K can be 1, exactly. So it says that if T1 and T2 and T3 and Tk, then Tk plus 1. It never told you that K cannot be 1.
Well, if it goes all the way up to T of K plus 1, then I think the
No,
problem is 2.
T of K plus 1 is on the right-hand side. It says if T1 and T2 and T3 and Tk, then Tk
Okay,
plus
yeah,
1.
yeah.
Okay? So K equals 1 is allowed according to this.
Yeah.
I think you should be prepared for it because I'm sure that data sets will have it. You're welcome to risk it and interpret it, but that's a minor problem as far as I'm concerned. Okay?
I was just asking the rules because when I was solving.
My interpretation is that the first one is allowed. I don't think it makes any difference to whatever I'm going to tell you, whether it's allowed or not allowed. Okay? All right, so here we are. So remember, if your statement is if something and something and something, then this, it's simply going to be an or, where you will have the complement of everything on the left side and the right-hand side. And everything will be separated by an or. Is that clear? Okay. Now let's consider this guy here. If spinach or feta, then pepperoni. What's that going to look like? So first of all, I can write this. S or F implies P, right? When I expand this out in this form, what happens to it? What does it look like? Right? So instead of or, it should be an and here, right? Everything else will be the same. Now, this can be interpreted, remember this is you can now distribute this and write it in expanded form as S or P and F, not S or P and not F and P, not F or P. So remember that the or case is a little bit, is going to look a little different. Is that clear? But I'm going to leave it this way because it turns out that's enough for us to understand. Any questions about this? Okay. So we're going to use, one way to think about this, and it's kind of useful, at least it helped me, is to think of this in terms of these logical trees. So any expression can be written as, at least the expressions we are going to deal with here, they will sort of look like this. I have an or at the top or an and at the top, and then I have, so that is the or of these two terms, this is the and of these two terms, and this is the not of this. So what you have here is that the leaf nodes, oops, what happened to it? Went away. Okay, it came back. So the leaf nodes are all variables, right? Boolean variables. In this case, should I have the topping or not? And all the internal nodes are Boolean operators, either not, and, or. And many Boolean expressions, at least in compilers, get written in this form, and so it's possible to write all these expressions in this manner. Is that clear? Okay. It helps me because now I can understand this in a different way by saying that I eventually want each of these expressions to be satisfied, which means I want a true over here. And the question is, what do I assign to these variables so that that becomes true? Is that clear? So I could have either true or false here, true or false here, or true or false here. Immediately, you can evaluate it, because this is going to be not of whatever it is. This is going to be not of whatever this is. And then this will be the and of these two things. And then that will be the or of these two things. Right? So it's possible to evaluate. You will have a true or false answer up at the top. And if you want this constraint to be satisfied, you want the top to be true. Right? Okay. Then we're also going to have some force constraints. These are the absolute constraints. The absolute constraints say, I have to have pepperoni. I'm sorry. If that is the case, this is going to be on, this is going to be true, in which case we're all set, because this thing will evaluate to true already. Right? So it's possible to simplify this or reduce these structures by deciding what those values are. This kind of helped me, but in the end I didn't use these structures. I'll show you how I thought about this. Any questions? Okay, so my first idea was to go with this structure that we had and then try and do some kind of a bottom-up computation. In the end, it didn't work out because many of the variables can be shared in these different constraints. So pepperoni may show up in different constraints, and it could mess things up for you. So it becomes very messy if you're just trying to do some kind of a bottom-up computation. So it turns out you can do something much simpler. So here is how this goes. Before I go there, are there any thoughts? Do you have any ideas on how we should approach this problem?
First, I'll say one that was in the live stream.
Yeah.
What Christian did, he took all, make sure I'm saying this correctly. And he collected all the sequences.
Yeah.
And he verified the ands first, and then he did the ors.
Okay.
That's how he did it. And then for me, I first tried brute force, but then after that, I was thinking of topological sorting it, which I'm not sure it would work. But yeah.
Okay, these are good ideas. Yeah. So let's see what I have here. Any other thoughts? Yeah.
I tried the same thing. At first, like, parse the input and then make that all the absolute ones, and then the ones that are not absolute as strings, but then somewhere in strategy try to process.
So you did the absolute ones first?
Yes, and then take the other ones, the ones that are the
Okay.
last.
Okay. All right. Okay. Good. So you guys are on the perfect track. One thing that might help you with a lot of these computations is to figure out what the data structure should look like. One of the data structures you're going to need is, if I give you a variable pepperoni, it would be useful to know what are all the constraints it shows up in. Okay. So imagine that you have one data structure that helps you to do this mapping. At the same time, well, actually, that's one. There may be one more, but we'll look at it later. I like the idea of going with the Singleton constraints first. These are the absolute constraints, because there the variables are fixed. You don't have a choice. You better pick them. So the other data structure that I was thinking of was to have something like a queue of all the variables that have to be set to where you already made a decision. So the ones that you're going to obviously make a decision on are the ones that are absolute constraints. So I put them on a queue. It doesn't matter in what order I put them. I'll just stick them there, and then I'll process them one by one. But as I process them, I am going to figure out which other constraints it shows up in and how it impacts those constraints. Okay, So therefore, the next step is going to be all the forced constraints. That doesn't mean these are AND constraints or constraints. All we are saying is, does it decide this constraint immediately? So if it's an AND, then remember, there's an antecedent and there's a consequent. There's a left side and a right side. Left side is T1 and T2 and T3 and Tk. All of them have to be satisfied. All of them must be already forced or decided. If that happens, then the right side is fixed. That is what I'm going to call as a forced constraint. So if the entire left side is satisfied or is decided, then I would call that a forced constraint. It's going to make one more variable a forced variable or decided variable. I will immediately put that onto the queue and say, okay, this one is decided. I have to pay for it, and we'll figure out what are the consequences of that being decided later on. Okay, so every time I process a variable, I'm going to see what other constraints get forced. And for each one of those, I am going to put that into a data structure that will continue processing. Now, what about the OR constraints? So if I have something like if T1 or T2 or T3 or T4, blah, 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 then T of k plus 1. In this case, even if one of the variables on the left side is turned on, right, then I have to pay for the right-hand side. This is another forced constraint as long as you have one of them. So the moment you see the first variable being forced, immediately you take this constraint and put it in the queue of things that need to be processed. So the right-hand side becomes forced as soon as even one thing on the left becomes forced. All right? So what we're going to do is we're going to go through each of the constraints, figure out if anything is forced. If anything is forced, a new guy goes into the set of variables that are now forced. And I will process that. And if something else gets forced because of that, then new things might end up going there. So I have to iterate this until I go through an iteration where none of the constraints are forced. In the end, I'm going to be left with a set of constraints where none of them are forced. All right? Which means I have an AND on the left-hand side where not everything is turned on. Or I have an OR on the left-hand side where nothing is turned on. Right? In the AND, unless everything is turned on, the left-hand side is not satisfied. In the OR, even if one of them is satisfied, left-hand side is satisfied. So I'm going to be left with a bunch of constraints that satisfy this. And the good news is that those are constraints I have to do nothing about. I can stop right there and report the answer. All right? So now let's go through the examples and see if this makes sense. Here it is. So let's start with the first guy here. All right, so I'm going to say, oh, what happened here? Oh, okay, I have to get out of this. Yeah. So let's look at this first example. What did I call them? I forgot already. These are the singletons. So I have pepperoni, sauce, spinach, and feta. And I have only one if statement. So when I process P, I'm going to check here. It doesn't impact this at all. So that's taken care of, so I have to pay for it. So I set up a counter to to say I'm going to pay for one topping. Then I will look at spinach and check. Spinach doesn't finish this left-hand side, and so I'm going to up my counter to 2 toppings. Then when I come to feta, I see again that this has no impact on this constraint, so I end up paying for this, and I have nothing more in the queue, and I stop here and I report 3. Okay. Now let's do the second example. The second example, I have pepperoni, pineapple, and ham. These 3 are the singletons, so I'm going to put them on the queue, right? So let me also improve my data structure. I'm going to call this 1, 2, 3, 4, 5 constraint numbers. So pepperoni shows up in constraint number 3. Pineapple shows up in constraint number 5, and ham shows up in constraint number 5. Okay, all this information will be maintained in some data structure. So I'll process these guys in the order in which they show up in the queue. I look at pepperoni, so I'm now paying for my first topping, and I see that it's contained in condition 3, and over here I'm also going to now say, so I'll say that 3 and 5 initially had 2 antecedents, meaning 2 conditions, 2 constraints. This also had 2, and now this becomes 1 because one of them I have satisfied. Does that make sense? So if I look at number 3, it says if pepperoni and sausage. Since pepperoni has now been paid for, it's a topping that I'm going to choose. I have satisfied one of the things on the left-hand side. There's one more left to be taken care of later. So that's the situation. Then I process pineapple, and pineapple now becomes 2. That's the second topic I pay for. And pineapple, this one, so this says it's in constraint 5. Constraint 5 had 2 of these, so pineapple will only take care of 1. And so I am now ready to look at the third condition. The third one is ham, and of course I will pay for it because it was required. And it's in constraint number 5. Constraint number 5 only has 1, and that must be ham. Since it's taken care of, the moment it becomes 0, whatever was the right-hand side of 5, which would be bacon, goes on to the list of things that need to be paid for and become forced. And so the next iteration, I'm going to pull out bacon, and that'll become topping number 4. Bacon is not on the left side of any of the things, so I have nothing more to process, and I can stop. And I will output 4, which is the number of toppings here.
Yeah. So we consider.
Sorry?
So we consider every non-if statement blindly, right?
Yes.
Non-if statement, we just
You're talking about these singletons.
Yeah.
Yeah, singletons will be,
consider no matter what.
yeah, I have no choice.
So and then you're gonna pass those if statements and check whether you have those toppings in your
Correct.
and
But I'm going to do that in every iteration. I'm going to look at every constraint in every iteration. Okay? If there is a smarter way of doing it, and there might be, we could make it faster. But this is where it's important to look at how many constraints and how many toppings. There are 1,000 constraints and 500 toppings in the worst case. So if I do it this way, I'm going to look at every constraint 500 times, because for each topping I'm going to do this, right? So the total time complexity in the worst case is going to be 500 times 1,000, okay, which is manageable. Is that clear? All right. So should we do the third sample also, just to make things clear, or is this pretty clear? Yeah, let's quickly do this. So this one says there's pepperoni and there's sausage, and pepperoni and sauce. Pepperoni is in 3 and 4. Sausage is in only 3. Oh, sorry, it's not 3 and 4. It's just 3. Yeah. Well, I will also need to know that mushrooms is in 4, and peppers is in 4. All right. So I'm in my data structure, I'm going to put pepperoni and sausage because those are the two singletons. When I process pepperoni, this will be my first topping. I will go to constraint number 3, and constraint number 3 has 2 things on the left-hand side, and constraint number 4 also has 2 things on the left-hand side. And in this case, we're going to do, since pepperoni is taken care of, this will become 1. Right? And then when I take care of sausage, it's going to, sausage will be paid for, and sausage is on constraint 3, so this 1 becomes a 0, which means whatever is the consequent of 3, which would be mushrooms, now needs to be put over here. Right?
So you're gonna do any string comparison, or else we're gonna hash them and store it?
Yeah, in this case, it's probably the simplest thing is to hash it.
So hash every string.
Yeah, that's what I would do.
And look up.
Yeah. So when I process mushroom is in constraint 4, and constraint, so this gets paid for, that's 3, and 4 this will become 1 because the first one of the left-hand side constraints is satisfied now. The moment this is paid for, remember, because this is an OR constraint, even if 1 is paid for, that whole thing is done. In fact, instead of 2, here we're only going to store a 1 because this is an OR constraint. Whenever you have an OR constraint, I'll just keep the number 1. And so the moment this becomes 0, I know this is a satisfied constraint, and so cheese goes over here. Okay? And then when I process cheese, I have 4th one, and you'll see that cheese is not on the left side of anything, so it's not going to impact anything. And at this point, I can stop, and you get 4. So this may not be the most efficient way to do it, but given the numbers that you're provided, this is completely okay. Is that clear? So if I were you, I would figure out in your head or on paper or in code what the data structures are and how you're going to connect these things and how you're going to do the hash. It's probably not very difficult, but it's worthwhile to go through the exercise. Yeah, you have a question?
Yeah, so the statement we only have single operator, or it could be either and or.
It's either and or. It's not a combination of and or. There are no knots on the left-hand side. So yeah, it's relatively it's much simpler than what you would than the more general Boolean expression. That helps because otherwise you're going to end up with combinations that you have to deal with, or something horrible. I'm not even sure. Okay.
To be clear, let's say I'm using a regular expression. I'm dividing it by particular word like if and. None of these toppings are going to have any of those letters combination. I mean, I don't know, because I tried doing this in this way. I think the problem said that the toppings won't.
Toppings will never be called if or and.
Well, they won't have them contained within the token.
No. Well, it doesn't matter. No, it might be. Meaning you're saying, can I have a topping called quiffer or something like that, whereas IF? That's completely possible. That's completely allowed. but you're going to look for spaces in order to figure out whether the end of the word happened.
So I think would be the best idea is to strip by spaces first.
Right, but the good thing is that the first word is either an if
Yeah.
or it's some name that's not an if. If it's not an if, it's a singleton for sure. If it is an if, throw it out, then you look for the then. Right? Until you hit the then, these are all constraints. In between, you'll see either and or.
I'll try that.
Yeah.
By one.
So yeah, if you look for the first space, then you'll know what the next token is. Okay. So are you pretty clear about this? This was easy enough? Okay, I have only 5 or 10 minutes, so let me talk a little bit about common factors. Okay. I don't know if any of you looked at this one. Let me see if you did. Common factors. Let's see. So looks like only one person tried it. So let me show you what this problem is. How many of you have looked at it, by the way? Any of you looked at it? Okay, good.
Wait,
good.
which one? Oh, common factors?
Yeah.
Yeah.
You
I
looked at it.
looked
Okay,
at
good.
It, yeah.
So this is the problem. I'm going to put that on the board for a couple of minutes.
Oh, I saw it.
You did see that, right?
Yeah. The hardest part was like putting it into putting a division sign, simplifying it. That was insane. There is a formula, like when you grab the formula, it becomes very simple. But then putting it into like 2 over 3, like printing that is extremely hard. At least in my opinion.
Printing what? Oh, you mean this slash sign?
Yeah, like the 2 and 3, because you could get an answer that would be like that would represent 0.66, but then to convert that into 2 out of 3, that was a pain.
Oh, I see. Hmm.
And also you have to simplify sometimes.
You may have to simplify. This is true. If you have 4 over 6. Okay, I had not thought of that, but I'll tell you some. So you solved the rest of the problem, and your only problem was output?
Yeah.
Really? Okay, good. Yeah.
Wait, if we do the division and it's a double, can we just not like add that string, like whatever the top one is,
So-
and then forward slash the
So
bottom one?
typically what you do is so your question is, if I have something like 12 over 15, how do I reduce this? Right? That's your question.
So can you repeat that, sorry?
If you have something like 12 over 15, you want to know how to reduce this.
Yeah, not only that, but like your normal output when like coding it would be in a floating point, right? So there would be a decimal, like a point.
Why? No, I can definitely have it this way. So where does it say that the output needs to be? Oh, it says a fraction in lowest terms. Oh, darn. Okay, all right, now I see. So yeah, so the reason this is possible is because this is a count and this is a count. They're going to be separate variables. You don't try to mix them until the very end when you're about to print. So I'm going to have this number separate from that number, and if I have to add or multiply, I will always work with fraction. So you can use fractions and do the arithmetic, and I'll show you how that works. And so the only problem is the reduction, which I don't see offhand, but maybe I'm sure we'll figure that out. Okay, so everyone read the problem.
I have a question.
Yeah.
If the greatest common divisor of P and Q is 1,
Yeah.
can there be a reduction?
No.
So if we just take P and Q, and that gives us a floating point number,
Yeah.
we know just
So
take P
you're right. That is.
forward slash and then Q.
That's
We
right.
don't have to
So
divide.
that's the answer. In fact, you just gave me the answer. So what you do is the following. If you can keep this separate, A and B, the lowest, the most reduced version of A over B is you do A divided by GCD of A comma B, and B divided by GCD of A comma B. Okay, that's the answer.
Yeah, but another issue was not only that, but even putting it in 12 over 15 form. Because sometimes
Yeah, but that's a trivial thing, because you're trying to get a number out of this, which is a bad idea. You keep A and B separate in two different variables. You don't combine them. Okay, and only at the end, when you're about to print, you can go and do this and print it out. Where you first print this, then you print the slash, then you print this. Very simple. Okay, does that make sense?
Yeah.
Okay.
I think it'll make more sense when we take it out.
Okay, all right, yeah. Okay, so, yeah, toppings have to go. This has to go. Where's the third guy? Yeah. So someone wants to summarize the problem quickly?
So you have a number, you go from 1 to that number, you find the two greatest numbers P and Q, where the greatest common factor is 1. So they're effectively co-prime. Is that the definition of it, if I'm not mistaken?
So you want to know how many are not coprimes,
Yeah,
right?
to get the ones that are.
Yeah. So you want to know what fraction of the numbers here have a factor in common with n. We'll keep that separate from n because we can always divide by n. All right? So, all right, so here's the problem. We are told that f of n is the number of integers in the range 1 through n that have common factors with n. I'm writing this in math notation. It's the number, it's the size of this set where m is such that the GCD of m and n is larger than 1. If it is equal to 1, then they are relatively prime. If it's larger than 1, then they have a common factor, and so that should be counted. Okay? So we are interested in how many of these numbers in the range 1 through n have a common factor with n. Fine? That's f of n. Then we are told that g of n is simply f of n divided by n, so it's simply a ratio. We will never compute g of n until we need it. Okay? We'll keep that on the side. We'll only work with f of n. And then I'm going to define a third thing that says h of n is the largest value of g of k for k less than or equal to n. This is what they really want as output. Right? So far, so good? Okay. So what do we know? The biggest hurdle, the biggest pain here is that this number n can be obscenely large. 10 to the 18 is just obscene. I mean, that's way too large. So you can't go and try every number between 1 and 10 to the 18. That's not going to happen. Right? If it's somewhere near 10 to the 6 or 10 to the 7 or even 10 to the 8, it's possible. 10 to the 18, forget it. Right? Okay, so this is our biggest hurdle, which means we cannot do something stupid like trying all the values of n. Simple. So here are some observations I should have, yeah. Since we are short of time, let's take a look. So let's start with the number 2. Here is my numbers between 1 and n. Here's 1, here's n. If 2 is a factor of n, what does that mean? If 2 is a factor of n, it means n is an even number. If n is an even number, then how many numbers between 1 and n share 2 as a common factor? How many of these numbers, half of them, right? So you have 2, 4, 6, 8, etc., and then this. So you're crossing out every alternate number. All these are going to share a factor 2 with them. So what we're going to do is to cross out things that share common factors. And those common factors, it's completely fine for us to work with prime numbers, right? So we're going to work with prime numbers in some order. And for each of those, we're going to cross out as many things as possible and count how many we crossed out. Simple. So what we're saying here is that half the numbers are going to share a common factor with n as long as n is an even number. Now, in fact, you can generalize this to say, if you, instead of 2, if I use m, and if I told you that m is a factor of n, or at least m, yeah, if m is n is a multiple of m, then I will have exactly n over m numbers that share factors, this factor m with n, right? So I could cross out every mth number, so I'm going to cross out n over m such numbers, right? So it doesn't have to be 2, as long as this thing is m. If the first one is m, this is 2m, 3m, 4m, 5m. All of these will cross out all the way up to n. It works out as long as it's exactly a multiple of, n is a multiple of m, right? Is that clear so far? So now let's do something simple. What happens if I want to say n is a multiple of both 2 and 3? How many of the numbers will share either 2 or 3 as a common factor? Right? That's what we want to figure out. And that's the calculation you see here. Remember, n over 2 numbers will share factor 2 with n. N over 3 numbers will share factor 3 with n. However, there's going to be some overlap. So therefore, the total number of common factors that you can cross out is not n over 2 plus n over 3. It's going to be less than that. Is that clear? Because things like 6 are multiplied by both 2 and 3. You can't count that twice. And this tells you exactly how many it's going to be. How did I get this? Well, first I cross out everything that shares with 2. That's n over 2. Then I look at all the things that share a factor 3 with n. And of these, half of them are going to go away because they are going to be even numbers, meaning they have share a factor 2 already. So this many will already share a factor of 2 with n, so the remaining is going to be another half. Did that make sense? Okay, you guys are staring at me. All right, let me do it here. Here's my number n, right? This is n, this is 1. Let me also put 0. So what do I do with 2? I cross out every alternate integer, right? So I'm going to cross out 2, 4, 6, 8, 10, 12, 14. Let's assume n is 16. Okay? Now what happens if so all these numbers share factor 2 with n. Clear. Now let's look for 3. We want to know how many of these numbers share the common factor of 3 with n. And we're going to assume that n is a multiple of 3. If that's the case, well, I picked 16, which is not a multiple of so I will go up to 18 here. What happens if I do 3? Well, here is 3. Then I'm going to get 6. Then I'm going to get 9. Then I'm going to get 12. I'm going to get 15. Then I'm going to get 18. right? How many triangles were there? Well, it's n divided by 3. But how many triangles also had a cross on it? It's half of those, right? Because we knew from the previous argument that any time you have n, half of them are going to share a factor of 2, right? So that's what I did here. Half got thrown away, so the other half remains. That's the n over 3 multiplied by a half. So you add that to your n over 2. That's the right answer. Is that clear?
So half of the 6 triangles
Correct.
got thrown away?
They didn't get thrown away, but they were already counted.
Oh,
See, this guy had an x, so it was already counted. This was already counted. Why count them again? So 1 half of the triangles were already counted, and I can ignore it. Same with this guy here. This is also going to have both the x and the triangle, right? So this tells me how this is done. Now let's add one more prime number. What happens if I also bring in 5? Tell me how I'm going to do the calculation. Remember now, if I have 2 and 3 as prime factors of n, then the number of common factors in the range 1 through n is 2/3, right? Is that clear? That's what we said. So 2/3 of the numbers are going to share a common factor with n. Some will share 2, some will share 3, some will share both. All right, now I'm going to ask, what if I have 2, 3, and 5? How many numbers are going to share a factor with n? Yeah.
I did how many factors of 2 plus how many factors of 3
Right.
plus how many factors of 5 minus how many factors of 6 minus how many factors of 15 plus how many factors of 2 times 3 times 5.
Right. So by doing that, you now have to try every possible combination of whatever was left.
Yeah.
Let me show you a simpler way to do this. Okay. Did everyone understand what he said? So you take n over you take how many are multiples of 2, how many are multiples of 3, how many are multiples of 5, add them up, and then you subtract out things that that occur in more than one of these lists, right? Which is what he did. Now that's fine with 3. But if you have 7, then the number of combinations becomes too much, and it starts to become a pain to look at pairs and triples and quadruples and so on. So instead, we're going to do it in the following way. So first of all, we know that if you only look at 2 and 3, I get 2/3. 2/3 of the guys have either 2 or 3 as a factor. I'm going to add to this n over 5. This is an overestimate, but that's the number of possible factors that share 5 with n, right? But I know this is going to be an overestimate because some of these are going to have been counted here. How many got counted there? That's the trick. And here what we're saying is something very simple. We are saying if you look at these n over 5 things, 2/3 of them, just like with n, remember here we said with n, 2/3 will share 2 or 3. So the same thing with this n over 5, 2/3 will share 2 or 3. What's remaining is 1/3. So it's n over 5 multiplied by 1/3. And I just add that to 2n over 3, and that's my answer. Okay. Now can you do 7? Can you do 2, 3, 5, and 7? What do I do?
Is it going to be 11n over 15?
So it's going to be 11n over 15
plus n over 7, you said?
plus n over 7, yeah,
Times
4 over 15, right? Because you've used up 11 over 15, they're going to be counted twice. I only have to account for the 4/15. And it turns out that's the right answer. So this is just the basics. This is not even getting close to what we really need to do. But you can go and check this out, by the way, and that's the right answer. Now, the trick here, how am I doing on time? So the trick here is that
You're actually over a little bit.
I am over a little bit, right? Yeah. Yeah, I am way over a little. So let me just finish, and you guys can go home and think about this. If it turns out that if I do these calculations for 2, 3, 5, 7, 11, etc. So let's say I stop at 11. And I try another one with 2, 3, 5, 7, and 13. OK? Well, actually, I'm just complicating things for you. Let me make it simpler. Supposing I try the combination 2, 3, 5. I know the answer is 11/15, right? Supposing I try 2, 3, 7 instead of 2, 3, 5. The question is how many, what kind of fractions will I get? And it turns out that this number is always larger than this.
Wait, which numbers are we going to?
This is the number of numbers that have common factors with n and 2, 3, 5. This is the number of numbers that have common factors with n from 2, 3, 7. This number will always be better than this number. OK? This is just, you can prove it more rigorously, but if you play with it enough, you'll see it. And so if I want, what were they asking? If I want all the numbers, let's say between, if I look at n equals 100, I want to know how many, is there some guy here which has the best score of g of n amongst all of this? So here's the way to do it. I'm going to take 2 and then multiply it by 3 and multiply it by 5. So I get 2 times 3 is 6. 6 times 5 is 30. If I multiply by 7, it already goes over 200, over 100. So these are the only 3 primes I'm going to deal with. And anything that has 2, 3, 5 as the factors is the answer. And so therefore, the correct answer is going to be 11/15. And the right guy that has that behavior is number 30. So between 0 and 100, the best g of n is achieved by 30. And it's going to be 11/15. All right? Now, that's kind of hard to believe. So if I make this 1,000, right, I'm going to go one more level here, times 7. That'll be 210. And if I do by times 11, that's already too much. So now 210 is the number with the largest g of n in 1 through 1,000. And the value is going to be this. So by the way, in order to solve the problem that you are facing, I'm going to work with, let's say, 210 or 30. I'm just going to count how many are common factors with n, and then keep track of that and keep the numerator and denominator separate. And in the end, I'm going to do this trick to print it out. OK? Yeah. Yeah, I know it's way over time, so let me stop here.
Thank you, Professor.
Oh, you're welcome.
Bye.